Welcome to the lecture series on numerical methods, finite difference approach. And in this lecture series, we have discussed in the last lecture that how we can just solve this two-dimensional parabolic equations using explicit method and Crank-Nicolson's method. And in this lecture, we will start about these parabolic equations in two dimensions using alternating direction implicit method or ADI scheme. So, specifically if you will just go for this parabolic equation, so it is written in the form of like del u by del t equals to del square u by del x square plus del square u by del y square, where we will have this prescribed boundary conditions at x equals to 0 and x equals to a, or the last boundary of x, and y equals to 0 and y equals to b, that is the first boundary along the y axis and the last boundary along the y axis. And initially we should have to provide like this t equals to 0, all these initial guessed values at the first boundary level. And afterwards we can just use this boundary conditions in the x direction or y direction, keeping t changed, but this boundary conditions should be fixed there. So, alternating direction implicit method suggested by Fishman and Rashford in 1995. This is a combination of explicit and implicit method, so that is why it is called a semi-implicit method. This method is also unconditionally stable, since already we have discussed that this Crank-Nicolson scheme is also unconditionally stable. And the method is performed in two stages. In the first step, we are just moving half time step in the x direction, and in the second step we are just moving half direction in the y direction. And afterwards we can just go like half time step in the x direction, again we will just go like a half time step in the y direction. And in a combined form, like a zigzag form, we are just obtaining the solution, and finally in a coupled form we are just obtaining a converged solution. So, these two stages we can just consider for this ADI method in a combined form if we are just considering two intervals at a time. So, the boundary conditions may be prescribed in the form of like u of xy 0, this equals to g of xy at t equals to 0, and some kind of boundary condition that can be prescribed at x equals to 0 and x equals to a, y equals to 0 and y equals to b. Especially we have discussed that three types of boundary condition, especially we are just applying for these partial differential equations. First one, it is the Dirichlet boundary condition, second one is the Newman boundary condition, and third one is the mixed derivative conditions. Suppose here like Dirichlet conditions are prescribed at all these boundaries. This means that u equals to some u specified values, it is just given along the boundaries. So, alternating direction implicit method or ADI method can be described in the following steps. In the first step, like Crank-Nicolson scheme, the discretization of this equation, that is in the form of like del u by del t, this equals to del square u by del x square plus del square u by del y square. At the mesh point, if you just consider like I, j, k plus half, and suppose we are just considering like I, j, k plus half. If we are just using Crank-Nicolson scheme, especially we are just considering this term in the central difference form, and this just takes the coordinates as I, j, k, and it is just next k plus 1, and next it is just taking the coordinate as I, j, k there. But if we are just considering the space derivatives here, so then we are just taking the average of this space sizes in the x direction in the kth level, and x direction and y direction derivatives in the k plus 1th level, and average we are just considering to get it in a compiled form. So, one derivative, that is del square u by del x square, is approximated at unknown level for this scheme, and other del square u by del y square is approximated at the known level. So, especially if you will just go like Crank-Nicolson scheme there itself, you can just find that we are just considering average of this one and this one at a particular time level, and plus this one at the next time level. But especially here in this case, we are just marching, if you will just see here, this x space coordinate in the I, j, k plus 1 level, and y space coordinates at the ijk plus ij kth level here. This means that half of the time step we are just moving in the x direction, that is at the unknown level, and half time step we are just moving in the y direction, that is at the known level. So, if you just neglect this truncation error for this series here, then we can just obtain this series as, if you just take this forward difference approximation for time derivative here, this can be written as uij k plus 1 minus uij k by del t here, and this space coordinate x, that is at k plus 1th level. So, it can be written as ui minus 1 j k plus 1 minus 2 uij k plus 1 plus ui plus 1 j k plus 1 by del x square, plus this space coordinate in the y direction at kth level here, that can be written as uij minus 1 k minus 2 uij k plus uij plus 1 k divided by del y square here. And if you just combine all these terms, and if you just keep these unknown parameters in the left hand side and the known parameters on the right hand side, then this system of equations can be written as minus del t by del x square ui minus 1 j k plus 1 minus 2 uij k plus 1 plus ui plus 1 j k plus 1 plus, since one coordinate it is just associated with this time derivative there. So, that is why it can be taken this term as in the form of uij to the power k plus 1 and one term here uij to the power k here. And especially we are just specifying del t by del x square, that is as r1 here, and r2 as del t by del y square for I equals to 1 to m minus 1 and j equals to 1 to n minus 1. And if you will just write these coefficients r1 and r2 as del t by del x square and del t by del y square, then this equation will be reduced in the form as minus r1 ui minus 1 j k plus 1. So, 1 plus 2 r1 uij k plus 1 here, since we are just minus sign is multiplied here. So, that is why it is just taking the plus sign there itself, and one more uij is present there. So, that is why it is just taken at 1 here. So, last term it can be written as a minus is multiplied. So, minus r1 ui plus 1 j k plus 1, and the right hand side if you will just look at, so we are just obtaining uij minus 1 here and one term here itself. So, that is why it is just giving as 1 here. So, 1 minus 2 r2 uij to the power k plus r2 uij plus 1 here. So, if you will just move further like stage 2, so advancing like k plus 1th to k plus 2th level, we have to consider here del square u by del y square is approximated at k plus 2th level and del square u by del x square is approximated at k plus 1th level. If you will just see here this marching step here, so first we are just moving this x coordinate at kth level here, and we are just moving this one at k plus 1th level, again x coordinate in the k plus 1th level, again this is in k plus 2 level. So, likewise we are moving here. So, the direction of this discretization of space coordinates are altered now. Thus, we can just write here as del u by del t at ij k plus 1th level here, and del square u by del x square at k plus 1th level, and del square u by del y square at k plus 2th level here. So, if you just neglect the truncation error, then we can just write this one as like uij k plus 2, since we are just considering here this forward difference approximation. So, that is why it is just written as uij k plus 2 minus uij k plus 1 by del t, and the space derivative in the x direction, this is just discretized at ij k plus 1th level. So, all are k plus 1th level we are just writing, and the space coordinate in the y direction, it is just discretized at k plus 2th level. So, that is why all terms are associated with k plus 2th level here. So, if we will just combine all these terms in k plus 1 and k plus 2th level for x direction and y direction values, then we can just obtain this approximated equation as minus del t by del y square, this into uij minus 1 k plus 2 minus 2 uij k plus 2 plus uij k plus j plus 1 k plus 2 plus uij k plus 2 here. Since this k plus 2 is the unknown variables we have now. So, that is why this k plus 2 values we are just keeping, at the left hand side and k plus 1th value. So, that has been computed from the previous cycle of calculation. So, which can be put in the right hand side here. So, that is why this k plus 1th label values that are associated, that can be that is just kept in the right hand side here. So, which is in the form of uij k plus 1 plus del t by del x square ui minus 1 j to the power k plus 1 minus 2 uij k plus 1 plus ui plus 1 j k plus 1 here. And if you will just put here R1 as del t by del x square and R2 is del t by del y square for variation of j from 1 to n minus 1 and I is varying from 1 to m minus 1 here, then we can just write this coefficient that is in the form of like minus R2, then uij minus 1, then again this minus sign is multiplied with this minus 2. So, that is why this just give you 2R2 here, and one term it is just coming from here. So, that is why 1 plus 2R2 uij k plus 2 here, and second term if you will just see here, so that is nothing but minus R2 and this term is written here. Similarly, if you will just go for right hand side here, so ui minus 1 j k plus 1 here associated with this term. So, that is why R1 into ui minus 1 j k plus 1 here, and second term if you will just see here, so one term it is just coming from this one and minus 2 R1 and last term is as usual there. So, from k plus 2th level to k plus 4th level, again the stage 1 and stage 2 are repeated and so on, we can just go. Like in each of these iterations we are just considering like first step as like k to k plus 1, then k plus 1 to k plus 2. So, first level is complete up to k plus 2, then second level we can just move like k plus 2 to k plus 4. Since the next iteration we can just consider like space derivative x in the k plus 2th level and like space coordinate in the y direction, it can be considered in the like k plus 3th level. So, whenever we will just go like further half time step, then we can just write space coordinate of x at k plus 3 level and space coordinate in the y direction at k plus 4th level. So, likewise we can just proceed for different time steps, and if we will just consider this example for 2-dimensional heat conduction equation here, that is in the form of del u by del t equals to del square u by del x square plus del square u by del y square, where x is specified as lying between 0 to 0.75 and y is lying between 0 to 0.75 for each t greater than 0. With initial temperature, since we are just considering u as the temperature here, and u of x y is 0, that is at initial level t equals to 0, this value is given as 10 x y here, and the boundary conditions are imposed as u of 0 y t equals to 0 and del u by del y x 0.75 y t, this equals to minus u of x 0 t is 0 and del u by del y x at 0.75 t is equals to minus u. It is just given to us, and the question is asked use alternating direction implicit method after subdividing the domain into square meshes of size 0.25 and approximate this derivative boundary condition by forward and backward differences as required. So, if you will just consider this time step del t equals to 0.0625, make the computation up to 4 time steps. So, if you will just consider this problem with the specified boundary conditions, so then we can just write this domain in the form like del x equals to del y, it is just given as 0.25. So, that is why we can just formulate this domain as x is varying from 0.0, 0.25, 0.50 and 0.75 here. Y is also starting, that is 0, 0.25, 0.50, 0.70, especially you can just move this one to here and you can just write this as like x is varying from 0.0, 0.25, 0.50, 0.75 here also. So, y is just varying in this direction and x is varying in this direction here. So, for your compatibility you can use in this direction or the specified direction, it is just given in the slides. And the boundary condition, it is just specified as if you will just see here, that as x equals to 0, so it is just given as 0 here, and at last boundary x equals to 0.75, this normal derivative equals to minus u there, or del u by del x equals to minus u, and especially for boundary condition at y equals to 0, it is just given as u equals to 0 Dirichlet condition, and this derivative condition, that is del u by del y at the last boundary, that is just taken as minus u there. So, if you will just first consider this u of x y 0 equals to 10 x y here, suppose. Then first coordinate, if you will just see here, this is 0, this is 0, so it can take as 0 value here. And if you will just consider this first coordinate here, suppose, we will just consider here like u of x y 0 is 10 x y. So, if you will just consider like x equals to 0.525 here and y equals to 0.25 here, suppose, then we can just write this one at this point as, since this is the starting point, if you will just see here 1 1 point. So, u at 1 1 0, that is t equals to 0 here, x is the first coordinate, we can just write I equals to 1 there and j equals to 1 there. So, that means we can just write this one as x1, this is as y1 there, and we can just write 10 into 0.25 into 0.25 there. So, that is nothing but 0.625 here. So, likewise, if you will just consider here like 0.25 into 0.50 into 10, this is just giving you 1.25 here, and if you will just consider 0.25 and 0.75, this is just giving you into 10, this is just giving you 1.875. So, similar way all other coordinates it has been calculated, like 0.75, this is just reflects this point here into 10. This just takes this into this one into multiplied by 10 here. This just takes this one into multiplied by 10 here. So, likewise all these coordinates here. So, this one and this one here into 10. So, this value into this one into 10 here. So, likewise all these values has been computed at the initial time level and it has been fixed in the first plane there. So, especially if you will just see our previous slide, we have given a clear configuration that how this x coordinate is varying or how this y coordinate is varying, and t is just in the perpendicular direction, it is just varying. So, each of these planes, since in the first plane if you will just see, we are just fixing like t equals to 0 there, and at each of these grid points we are now have the values that is just calculated here. And for the next immediate step of calculation for del t, that is t equals to del t, we have to move to the next immediate step there. So, for this if you will just go for this next slide here. So, for r equals to 1, the ADI method can be written as like minus ui minus 1 j k plus 1 plus 3 ui j k plus 1 minus ui plus 1 j k plus 1. Since r is a 1 as considered here, so especially if you will just see here, so that r is considered as this is we have considered here, if you will just see here, r2 equals to r1 equals to 1 here, that is r1 is del t by del x square and r2 is del t by del y square. So, both these values are considered as 1 here. So, that is why r1 equals to r2 equals to 1 we have considered. So, if you will just put here r1 equals to 1 and r2 equals to 1 here. So, first coordinate if you will just see, this equation is written in the form like minus r2 u I j minus 1 k plus 2 and plus 1 plus 2 r2 u I j k plus 2 minus r2 u I j plus 1 k plus 2 here. So, if you will just see this equation here, you can just find that minus u I j minus 1 k plus 2 plus 2 plus 1, this is nothing but 3 here, u I j k plus 2 minus u I j plus 1 k plus 2. So, right hand side if you will just see here, so this is nothing but r1 u I minus 1 j k plus 1 minus plus 1 minus 2 r1 u I j k plus 1 plus r1 u I plus 1 j k plus 1 here. So, and of course, if you will just put all these values, then you will have this two set of equations whatever it is just written here. Since a first time step we are just calculating here, that as the values as like minus r1. So, first time step I can just write here also minus r1 u I minus 1 j k plus 1 plus 1 plus 2 r1 u I j k plus 1 minus r1 u I plus 1 j k plus 1 here. So, that is why r1 equals to 1. So, that is why it is just take these values in this form here. Similarly, this right hand side you can just get it from using this equation number 12.3. So, once we are just using I equals to 3 here, using backward difference for this boundary conditions, then we will have these conditions like u3j k plus 1 minus u2j k plus 1 by del x as minus u2j k plus 1. So, from there itself this boundary point, that is u3j k plus 1, this can be obtained as in the form of 0.8 u2j k plus 1 there. For j equals to 3, using backward difference for boundary condition, if you just see here, we can just write as ui3 k plus 1 minus ui2 k plus 1 by del y, this is as written as minus ui2 k plus 1. So, that is why this boundary point ui3 k plus 1, it can be written in terms of the domain values or the domain variable ui2 as 0.8 ui2 k plus 1 here. So, for t equals to like first increment, if you just consider here, so t can be written as like t0 plus del t, that is nothing but 0 plus 0.0625. So, that is why it is just written as 0.0625 here. And if you just consider like I equals to 1 to 2 here, for each j equals to 1 to 2 along with this boundary conditions. So, we can just write this values of temperature at different node points here. Here also you can just shift this one, j is varying from like 0, 0.25, 0.5, 0.75, and I can be written as like 0, 1, 2, 3 here. And if you just compute all these values from this set of equations that has been formulated here, then we can just find the temperature values at different grid points, that is 1, 1, this is just like 1, 2, 1, 3, this is like you will have 2, 1, 2, 2, 2, 3, then it will have 3, 1, 3, 2, 3, 3 coordinates. So, this is the computed values that has been computed by using this previous equations. So, if you just go for the next iteration step, we can just write t can be written as like t1 plus del t. Since t1 it is already calculated as in the previous slide as 0.0625, and incremented value del t equals to 0.0625 there itself. So, that is why this final t, or you can just write this one as a t2 here, that is nothing but a t1 plus del t. So, which is written as a 0.1250 here. And if you just go for this calculation of temperature here, so then this calculation we can just get it as like for first coordinate we can just get this one as 0.2343, and for like 2, 1 coordinate we can just get it as 0.2344, and third coordinate we can just get it as 0.1875. So, likewise further if you just move here, we can just get it as 1, 2, then 2, 2, then 2, sorry, this is like 3, 2, and then this is 3, 3, and this is like 2, 3. So, this is like 1, 3 here. So, all of these coordinate values like corresponding I and j coordinates, if you just put, and you can just obtain these values. So, for like further increment of this time step, if you just use like x coordinate as in this direction here and y coordinate as in this direction, and put all these values, then we can just obtain these values for temperature at a different grid points. And further movement for t, we can also obtain these values are in this form, and this can be tested easily since all of these calculations, this proceeds with 1 by 1, 1 by 1. So, that is why you can just compute and you can just find these values here. Thank you for listening this lecture.